What does a margin of error help us to do? Okay, it helps us to account for uncertainty. Okay, if we talk about a margin of error, it is often in political polls. Political polls, like who's ahead in the poll, margin of error. But it helps us account for uncertainty. They say 61% are in favor of raising the driving age to 23. Okay, hopefully that's not true. There is some degree of uncertainty. What is the margin of error? The margin of error is an amount, that's abbreviated, that is added / subtracted, from the main number good morning, added or subtracted from the main number to give a, what's the word I'm looking for? To give a range, I'm trying to think of the word that goes in front of that. A range of possible numbers. It is an amount or a percentage of amount that is added or subtracted from the main number to give a range of possible numbers. Okay? So, number 1 says, when conducting a survey, political analysts wanted to know how many voters will be voting for candidate A for the senator of Indiana. When using a random sample of voters, they determined 57% of voters are going to vote for candidate A. Okay, that's your main number. Now, there's some uncertainty in there. That is within a margin of error that's estimated to be 4%. What does this margin of error mean for the voters of Indiana? Well, here's what it means. That means we are going to have a maximum or a high number of 57%, that's my main number, plus 4%, which gives me 61%. Okay, so my maximum or high amount number is 61%. It also is going to give me a minimum or low number range, which is the number given, 57% minus 4%, which gives me 53%. Okay? So that means an acceptable range is going to go from 53% to 61% that are planning to back candidate A. Basically, we're saying we can't trust when people say 57%. So there's got to be a margin of error that goes higher than that amount and lower. We're on notes on page 14. Edgar, notes on page 14. Okay? Any questions about that? On the next page, we have another example of a number that's given, and we need to find the range The hardest part about all of this, it's a lot of reading and writing. Okay? A lot of reading and writing. All right, so let's take a look here. Number 2 at the top of page, what page is this? 15 says, a researcher surveyed a random sample of students from a large university about how often they talk to their parents. Using the sample data, this is the sample data, researcher estimated 12% of the students in the population talk to their parents. Okay? 12%. The margin of error is 3%. Okay? So that means your maximum or high amount is going to be 12% plus 3%, which gives me a total of how much? Come on, don't be shy. Actively participating, 15%. Come on, guys, you got to be active. You got to say it. Crystal does a good job of it. Okay? Maximum or high amount. Then your minimum or low amount is going to be 12% minus 3%, which gives you 9%. So whatever the margin of error is, you add that amount to get the higher level, you subtract that amount to get the lower level. The researcher is reasonably confident that between what range of students talk to their parents at least once per day? Is it A, 9 to 12, B, 9 to 15, or C, 12 to 15? Survey says B, 9 to 15. That is correct. Any questions about that? Okay, now when you talk to the sample, that's where you are getting this actual estimation of 12%, but you are projecting it to the whole population. So that's why there is a margin of error, okay? Just because it's true for the sample does not mean it's necessarily true for the whole population. All right, lots of definitions here, all right? Here we go. Theoretical and experimental probability. And I kind of tried to talk to you about this before. So theoretical is the ideal chance, please write this down, for something occurring in a perfect world. So pretty much everything we've been talking about is theoretical. It's theory. It's what it should be, okay? In a perfect world, okay? For example, okay? Flipping a coin. You don't roll a coin. Flipping a coin and getting heads 4 out of 8 times. That's what it should be because you have 2 sides and you should get heads about 1 out of every 2, half the time. So if you flip the coin 8 times, you should get heads 4 out of the 8 times. Okay? Experimental probability is the actual findings from an experiment. The actual findings from an experiment, meaning we actually did flip a coin, okay? And so my example here is I flipped a coin 8 times and got heads 3 times. So in theory, yeah, it should have come up half the times. But when I actually flipped the coin, I got heads 3 times. Okay? Now, the law of large numbers says that using experimental data, actually using the data when you flip the coin to predict what would happen, if you did the experiment, and we're going to put a lot in big all caps, a lot. Law of large numbers says using experimental data to predict what will happen if you did the experiment a lot. Okay? So, for example, if I flip the coin 8,000 times, that's a lot, I would get heads 3,000 times, because it is based on the experimental data. Okay? The experimental data, the data that you used when you actually flipped a coin. Okay? Questions on that? All right, so let's turn the page. Turn the page when you are done writing that down. I don't know if I can do this. Maybe I should do this. All this writing. Put it over here so you can see. All right. So here we go. It says, find the theoretical and experimental probabilities of rolling an 8. All right, so first up, theoretical. Okay, and over here we have experimental, where we actually did it. So in theory, of rolling an 8. This must be an 8-sided die then. They don't say that, but it must be. Right? Kind of weird. All right, so we have an 8-sided die. I'm going to put that up here. There's also 10 and 12. Any of you that game, I have sons that game. They're kind of nerds like that. That's okay. Good for them. Theoretically, okay, if we have an 8-sided die, how many sides are there on the die? 8-sided fair die. How many sides are there total? 8. Thank you. All right. And if you have the numbers on the die being 1, 2, 3, 4, 5, 6, 7, 8, okay, in theory, rolling an 8, the probability of getting an 8 on an 8-sided die, how many sides have an 8 on it? 1. 1 out of 8. And as a decimal, if you take 1 divided by 8 on your calculator, you're going to get 0.125. Okay? So this is the fraction form. This is the decimal form. Taking 1 divided by 8, this is the decimal. And if I wanted the percentage, I would go 2 places this way. It would be 12.5%. Okay? Experimental. Experimental says we are actually going to roll this die several times. This is a frequency table, which some of you did not do as well on the skills check. Okay? Frequency table. This is your data, the data that comes up. This is how often it comes up. Okay? So we got a 1 28 times. We got a 2 on our die 19 times. We got a 3 24 times. A 4 22 times. 5 21, 6, 18, 7, 26. We got an 8 42 times. That's crazy. What do I need to find here? If I'm talking about experimental probability, it is probability, right? So I need a numerator and a denominator. I need to know what? Starts with a T. Total, yes, thank you. So if I add these all up, don't worry, I'm going to tell you the total. It's 200. Okay? Where does 200 go in that probability? The numerator, denominator? Denominator, thank you. Excellent. So to get an 8 here of the experimental, the probability of getting an 8 in experimental, what does my frequency table tell me? How often did I get an 8? How often did I get an 8? Don't be shy. 42 times out of the 200 times total. Okay? If you take 42 and divide it by 200, you are going to get 0.21. Okay? 0.21. This is the law of large numbers. Okay? Using that law of large numbers, because we rolled the die 200 times, how many times would you expect to roll an 8 if you rolled the die 1,000 times? So this is going to come down here. This is 0.21. Remember, that is for 200 times. Okay? But we want to know what's it going to be when we roll it 1,000 times. So I need to take that and multiply it by 1,000. When you multiply a number by 1,000, you can do that on your calculator. Or since our number system is based on 10, you would move it 3 spaces to the right. And that number is going to be 210 times. Remember, it's not a probability, it says how many times. Okay? I gotta watch my time. Okay. So you know the theoretical, you count the experimental, you actually do the experiment. And once you get your fraction form, you change it to a decimal. Change to decimal. And then you take that decimal form times however many times they give you. All right. So now let's go back to October, trick-or-treat time. Says, after trick-or-treating, Devin had a bag with an equal number of Snickers, Reese's, Kit Kats, and Twix. He did really well. That's good candy right there. He selected one candy bar out of the bag, recorded his selection, and returned the candy to the bag. He repeated this process 150 times. Crazy. Or a real math nerd. Maybe a little bit of both, right? What is the theoretical probability of selecting a Twix? Theory. This is what it should be. Express your answer as a percent. Okay? After trick-or-treating, Devin had a bag with an equal number of Snickers, Reese's, Kit Kats, and Twix. He selected one candy bar out of the bag. So if he had an equal number, how many different choices did we have? How many different choices? What's my total number of choices here? On the bottom. We got Snickers, we got Reese's, Kit Kats, and Twix. He has an equal number of both. So we really don't need to know the total, but of those four, if he has the same amount, he has a choice of 4. Okay? Snickers, Reese's, Kit Kats, and Twix. He selected one candy bar out of the bag. So that's going to be a 1 on top. Express your answer as a percent. Well, it shouldn't be as a percent. I would say it should be as a decimal. We're going to cross out percent. Decimal. So if you take 1 divided by 4, boy, that's not even right. What is 1 divided by 4? I'm sorry, I'm looking at notes from another teacher. 1 divided by 4 is what? 0.25. Okay? This is in theory what it should be. This says he actually did an experiment now. Okay? What is the probability of selecting a Twix? He did this 150 times. Okay? So here's my Twix. So that 29 is my numerator. And do you remember what the total was? How many? Okay, there were 4 different candy bars, but then he did an experiment. How many times did he put that candy bar back in? 150 times. Okay, so that 150 goes here on the bottom. So when you take 29 divided by 150, hopefully you get, I don't know, what do you actually get? I might have a rounded answer. 0.193. And it says answer decimal to the nearest hundredth. Well, she did to the nearest thousandth. Is it 0.193 exactly? 3 repeating. Okay. So, given the law of large numbers, how many Twix would you expect him to select if the experiment was done with 1,000? This means you take this number, and I know it says hundredths. We're going to do it to the thousandth. And we say 0.193. I actually did the math. That's how often it came. Times, what amount am I going to do it for? What amount am I looking for? 1,000. So multiply that by 1,000, which means I am moving it 3 places to the right. And that means my new number is 193 times. Boom, drop the pen. We're done. All right. So, homework number 4 should be due, I think tomorrow. I think I said Wednesday, but I was thinking yesterday was Monday. We're off a day. Homework number 4 should be due tomorrow, which is Thursday. Homework number 5, I think, of course I don't have that handy. Does anybody have homework 5 handy, or their homework in general? What is this? What is this? Maybe this is it. There's 2. There's 3. Bias, margin of error. Homework 5. Homework 5 is theory and experimental probability. So you need to start working on this. I would say that should be due on Friday, if not tomorrow. Then don't forget, we have the weekly Canvas activity. Oh my gosh, so much going on. Yes, there is a lot. Tomorrow, how many of you have heard of mean, median, mode, range? Mean, median, mode. We're going to do a quick review about that too. Boy, we're just stuffing everything in here in this chapter. I know. It's a lot. It's a lot. And it is